Okay, so I'm gonna explain what persistent homology is, and I'm gonna go through how it could possibly be used for data analysis, uh, and the potential advantages that persistent homology offers when it comes to analyzing a data set. So, in order to understand persistent homology, we first need to understand just what homology is. Now, homology is generally pretty complicated to motivate it rigorously, but there is an intuitive understanding behind homology, and it's just a measure of how many holes the topological surface has in varying dimensions. So basically, you could say H0 of some topological space X, right? So this is some space, right? A topological space. And we should have some notion of what that is. And we'll go through some examples and we'll understand. But the H0 of some topological space X is just a measuring of its connectivity. Is the space connected? And if the space is connected, this is going to be isomorphic to Z. Okay? Now, if it's disconnected and it's two pieces, then what's going to happen is that there's two pieces to this, so there's going to be two of this Z, of the integers. There's going to be two. But if it's just connected, one space connected, then it's going to be Z. And that doesn't lend itself to the whole aspect of homology, but H1 actually does. So H1 is a measure of how many loops there are, the one-dimensional circle, or the two-dimensional hole, right? So it's going to be Z if there's one loop, and then this if there's two, and then this if there's three, and so forth. So an example illustrating this might be something like let's pick an example. So let's say let's say a figure 8, right? So we have some topological space. It's just two circles joined at a point, right? So something like this. The homology group for this here in H0, since it's connected, is Z. So this matches. And then in this case, since there's two loops that I can't shrink to a point, it's Z cross Z as the homology group of H1. Now H2, in this instance, is going to be a measure of, again, how many holes there are, but now we're going up a dimension. So this H1 was a measure of how many S1s there are, how many circles or loops, right? This is a measure of how many loops. And now this is going to be a measure of how many spheres or how many voids there are, right? And since this is like a two-dimensional figure, this is going to be 0, and going down all the way after that for any number, for any I greater than 1. In this instance, it's going to be 0. So we have, this will be isomorphic to 0, but then this is a measure of how many voids or how many spheres, right? And that's the three-dimensional hole, so to speak, and then this is like a two-dimensional hole, right? And then this is just a measure of connectivity. And going down, right, we can't imagine what it would be after, what we're talking about when we're talking about a sphere of 4 dimensions, right? The 4-dimensional sphere. So then therefore the 4-dimensional void can't be really understood. But the other homology groups, so this is the one where it's measuring how many spheres, and in my example of just this figure 8 configuration here, it would be 0. But and that's the intuition behind homology for a topological space. So it's better if we also do like a few like standard examples. So another standard example would be, let's say, a torus. So let's just get an understanding of what a homology group is. So the torus is your donut, right? It looks like this. It's a donut, and basically, if we were to try and just intuitively see what the homology groups are, H0 of the torus is Z because it's connected to one whole thing. You see, it's the number of integer groups that we have, right? This is addition. This is this group here. It's an abelian group composed of just the integers, and it's closed on. It's a group under addition, the operation of addition, and that would be the group. Now, it could be that you have two Z's, right? That would be the disconnected space. That would be like if we had another torus and we said, okay, well then now it's two toruses, these two things are disconnected, so we would need this other Z representing this one. So how many Z's you get tells you about how connected it is. So again, and if I put something like a loop over here and I included this everything as my topological space, then there'd be another Z here because there's three disjoint, not connected pieces to this, which is represented by the fact that there's three coordinates, or that this is the cross product of three Z's, right? And it gives you, again, this is a measure of connectivity, this first one, which doesn't really align well with the whole idea, but it is sort of a measure of holes in a weird way. But anyways, so H1. Now let's go and let's compute. Let's just go back to the original torus. Let's make sure we remember that we're only going to focus on the torus. I was just doing examples to illustrate the idea for other spaces, but we have here our torus. And if we do H1, right, what we're measuring is the number of loops that can't be shrunk back to a point. And in the torus, if you look, right, if you look at this loop that goes around and then the other way, and then there's another loop that goes around like this, okay, there's actually two loops that can't be contracted back to a point. So this here, H1, how many loops are there? There's Z cross Z. And then there's, since representing one of the loops. Now the question is what about H2 of the torus? And this is the measure of voids, or how many spheres can be embedded. And the answer to that one in the torus is that you could kind of see that there's the inside to this. The inside to that represents one sphere. And then you get Z. And then going on further from here, you get that the homology groups are all zero. These are isomorphic, but equal Z, isomorphic, whatever you want to say. But though they're all isomorphic, so then after that, how many four-dimensional, well, the torus itself is only a three-dimensional surface, so it's going to be zero going down further. Now, this is the homology groups, and again, we want to make sure we understand how we intuitively interpret this idea. It's just basically that this is a measure of connectivity. This is the measure of how many one-dimensional spheres, how many two-dimensional spheres, how many three-dimensional spheres, and so forth and so forth. We could do another example with just the actual sphere itself as a topological space. So example S2, right? That's the sphere, and if you look, H1, right, or H0 of S2 is going to be that it's just connected by one space, so it's just one Z there. But H1, unlike the other one, unlike the torus, you can't have a loop that you can't contract in the sphere. Okay, if I put a loop right here on the sphere, right, with the point right there, I could just pull in this to being smaller and smaller until it contracts to that point. So this is actually zero. And then H2 of S2 is that there's one sphere. There's the Z as the one sphere that you obviously have. You can't contract that sphere any further. And again, it's a measure of how many holes this is the intuition for homology. Now, we want to get to persistent homology and how it is that we can use this in data analysis. So the way it is that we go about this is that you typically in data analysis have some some data set in Rn. Okay, so Rn, right, the n-dimensional space. You have a variety of features, and then perhaps an identification and a target. Maybe not. Maybe it's just just some thrown data in Rn, which if we're talking about big data, it might likely be that. But whatever. We have some large data set. It's just a collection of points, and there's not much to say about the topology as it stands in that form. If you took, like, for example, let's just take a data set in R2 that looks something like this. So let's look at a data set in R2. So a data set in R2 where, you have something that looks like this. Okay, and I'm going to just hopefully try and get this done quick. Okay, so this is a data set in R2, and you can kind of see that it has some structure to it, right? It's like, are you going to predict that there's a point here? If we needed to predict something about this data set, no, you would likely say that doesn't seem like it's the case. You might want to predict that there's a point here, as opposed to in the center. And this data set has structure, it has shape that we could identify visually just by looking at it. But now, but topologically, as this data set stands, we can't say much. It's just a collection of disjoint points. There's, the homology group for this would just be however many points in H0. The homology group, if this is the space X, would just be Z, cross however many points we have, M, I don't know, if we have M points. And that would just be that, and then everything else would be 0 going down, and it would tell us nothing else. Okay? Everything would be 0, because there's no loops that we would have. We couldn't make a single loop, because they're all, again, disconnected. So what persistent homology does is it just creates you pick some epsilon greater than 0, and it could be any epsilon greater than 0, so it can be very fine, and that's maybe partially the key, because you basically choose epsilon greater than 0 to construct a ball around each one of these points. So the radius of this ball is epsilon, and you keep doing that. You make a ball around every single data point, and you see how it is that these balls now intersect with each other, or these spheres intersect with each other. Okay, and when they intersect, you follow certain rules. So if you have the intersection of two balls, you join a line between them. So for example, these two would be a line, these two might be a line, these two might be a line. But if you have three intersecting, so let me just draw it over here. If you have something like this, and then you have three all meeting together, so I'm going to try and just, you see, so they all intersect at that point right there. So these 3 points intersect each other. What you do is not only are you going to have the edges connecting these 3 points, but now, since there's that intersection among all three here, you create a face. And that's important. And then if we had 4 intersecting balls, you'd create the tetrahedron. Okay, so I'm going to explain that again. So it goes in order. So you have that on the one hand, you have that if you are in R2, let's just make it simple, and then you have, or Rn in this case, because obviously if I'm going to go into higher dimensions in a second, but whatever, you have some data set. You have a collection of 3 points. Okay, here's your 3 points. Now, in one case, you could have something like this, that the balls are small enough so there's no 3 mutually intersecting points, right, or balls, right? So there's some radius, epsilon, for each one of these balls. So this radius is epsilon. Now, you see, this ball intersects with this one, so you draw an edge to indicate that those 2 balls intersect. Now, you draw the edge joining these 2 because these 2 balls intersect. And then you draw an edge with these 2 because those intersect. And then you'd be done in this instance because the 3 balls do not mutually all intersect. But if epsilon gets a little bit bigger, then you see that region between all three. So if I do it again, where epsilon is slightly larger, right? So now epsilon is larger, and what you have now is that region where all three of these come together. So the edges will still be drawn. So you get the edges, but then the three will come together, and when the three come together, you don't just add an edge, you now add a higher dimensional level of connectivity among these 3 points, which is the face. You draw this face, and if you were to go into higher dimensions, if there was a point, like, you know, maybe up, imagine a point up here, right? And then you drew the sphere around it, right? And then the spheres all intersected. You would draw the tetrahedron and fill. You would draw the tetrahedron and fill it. Yeah, you would draw the tetrahedron and fill it if there was all four intersecting. But you could have the hollow tetrahedron if you have all three mutually intersecting, but not all four mutually intersecting. So it's this interesting way you could look at the connectivity behind all these points. But in our example, let's try and understand what it is that happens. So basically we have some epsilon, and I'm going to draw a ball around each one of these points. And there's going to be some connectivity among all of these. And I could have it that all three intersect, and then you connect the space in such a way, and then you look at what you have when you do that. And what you'd have is at least a loop as epsilon gets larger and larger. So at least a loop, because basically all of this will become connected. And you'll get that at the very least, that no longer is it the case. So first of all, you'll have h0 of x no longer being z all that times. You'll just get one z, because it'll all be connected eventually, or for a large enough epsilon, let's say, because, you know, maybe there's some gap here, and then therefore it doesn't, well, even if that, it would still be z, because they would be connected. But I mean, if let's say it was like really small epsilon, like for that one, and then this one were isolated by itself, everything else would be connected, but then this one could potentially be removed, which would mean that it's two pieces. But if epsilon is large enough, then all the points will be connected, you know, and it would just give you one connected space overall. But now from this, yeah, so now you're gonna have some connectivity, and you want to follow the rules that I just described. Even in R2, the most you could have is that you have a face, because we're only dealing with R2 in this case. So the most you could have is that you're pasting a face, but not the tetrahedron. Even a hollow tetrahedron wouldn't be possible. Is it? No, a hollow tetrahedron wouldn't even be possible. So all you get is at most a face. So maybe like I'll have these three intersecting mutually, so then I connect these with a face in all of them. And what you'll get is then you'll get something that's actually more akin to a topological structure that you could compute the homology on. So again, you would have that the connectivity now is z. h1 of x will be z, just one z. And then h2 of x will be 0, and everything else will be 0 going down. And it's easy to see that this is very similar to like an annulus. So this topological space, right, an annulus has the same homology. So this is an annulus, and this is similar, where it's completely filled in like this. So the shape of this space is very similar to these two, right, are very similar, the points, and that's what it does. It allows you to see this collection of points now as an annulus, but it also allows you to sort of see when it stops being an annulus, because what will eventually happen as you make epsilon large, as epsilon gets large, the homology goes away from being an annulus, because what happens is that if I make, you know, the radius ridiculously large, it's just going to fit all the points, and there's going to be a level of connectivity that allows everything to shrink to 0. So then what's going to happen is that if the, you know, it's going to be like this, let's say, I don't know, and then what's going to happen is that all of these are going to come here, and then the whole thing is just going to become this giant disk. And then once it becomes the disk, it could be just shrunk to a point, and that loop in H1 goes away. And that's a useful feature. And there's two main uses, or I feel that the utility behind persistent homology is in two major difficulties when it comes to data analysis. The two major difficulties that persistent homology can potentially help handle is the amount of noise that a data set has, and I'm going to explain why, the noise, and the fact that there's so much mathematical theory dealing with topological spaces, even in higher dimensions. We have theorems that we could use. In particular, if we could somehow use a more general version of the prime decomposition theorem, which basically says that every 3 manifold is homeomorphic to a very, to certain types, then, you could do that, but that would only be in 3 dimensions, so you're limited in that regard. But if there's more general n-dimensional theories that aren't as strong as that, they could possibly be leveraged, so it's a possible avenue to classify higher dimensional data. But in any way, there's just massive theory. There's just a lot of theory. And again, in particular, I would say just using the homology to potentially classify the surface would be good, because again, like, you could look for some epsilon, right? This is gonna have the same homology as the annulus, this data structure that I originally gave you. So you can then begin to speculate what the actual homology is, because you could even vary epsilon. So at first it's going to start off extremely disconnected with m, because epsilon's not going to be large enough for the points to see each other, and then they're going to start connecting, and then that's going to give you this z in the first loop going around, this loop in the annulus, this loop going around. But then what's eventually going to happen is that as it becomes too connected, it's going to bridge the radius, and they're going to all be connected, and then it's going to shrink to being nothing, and then this will go back to nothing. And you could look at the interval for that epsilon, and that's going to give you potentially relevant information, because the annual, you could see how you could then maybe get more structure on what the data actually looks like by varying epsilon. But the real thing that I think is the thing that this all goes to, that I think is interesting, is the potential for noise. So why is it that noise is interesting? So if we're talking about big data, right, we have something in 500 dimensions, and we're massive amounts of points of data. What you could potentially do maybe is scale it in some way, so that way you can utilize the fact that epsilon you can be super precise with. So you can make epsilon very, very small, and you can see where there's noise potentially, because it might be that there's noise pattern, or something insane nobody knows. But even in the case of what it is that I'm arguing with in R2, this data set, so you see I had these points. Let's see, dare I try and go back? Let's just erase. Let's just illustrate my point. So in this data set, right, so I'm going to just draw the data set again, more or less. In this data set, right, I had something like that, right? But an interesting fact is that what the data set might actually be, especially if there's a lot of data, the value in persistent homology could be in removing noise in the following way, in that it may be that if you zoom in, right, you get another annulus, and that this is just a cloud of points as well that are originally taken as being completely connected in the original ball, because epsilon was too big. So if epsilon's big, right, then it's just going to view this as a separate island, right? As a point, so to speak, even though it's a giant cloud. And you could zoom in, and then you could see that it's a cloud of points. That, you know, even though I can't really do it here, but this is an annulus, or even has some other topological structure to it, and that's good because, or it could be noise, right? This could be just noise. Like, this could be like a collection of points, and it's just random. And when if we make epsilon very small at first, we're going to see just noise in this original cloud. And then we're going to zoom out, and then you're going to start to see pattern in the actual annulus as you start connecting these, and then you see, oh, okay, it has these homology groups. It could be an annulus, theoretically, and that will drive us, again, to better understand the data set. And again, we could use the theory that's been developed for, you know, classifying topological surfaces to get a better understanding. But that's one route. Now, the other thing that we could potentially do is that if you do have a higher dimensional space, what you could try and do is you could just try to find a topological space that matches that exact homology that the persistent homology gave you. So then that way you can maybe say, well, the data might look like this topological space because they have the same homology. But that would potentially take time, and also you would want to run a whole bunch of computational, you would want to compute the homology for numerous topological spaces in that instance. But this could be done, and I believe that this is the two main benefits for it, because, and again, I'm just going to say one last thing on the noise or the randomness. The noise and the randomness, or randomness, whatever, noise, randomness, if you want, the difficulty to me seems that there's just so much randomness to this. And the pattern extraction is difficult because of that noise. So if we can find a way to find the right scale, and I don't know, I'm not sure what scale it would be where we can maximize pattern versus randomness, but this could be a potential method for finding out where there's noise and just disregarding it, that we're not going to be able to find any pattern in this because we can tell that it's noise, and then no, there's pattern when epsilon is nice. Again, like if I zoom in on one of these points, right, this, if we're talking about big data, this could no longer be a point. This could be a collection of points. This could be, I don't know, this could be like, you know, this could be looking like something like that. And we just can't tell because from back here it just looks like a point, and then when we compute the homology, the ball goes around here. All of that becomes connected into one giant, filled in, because you're going to draw edges around these, and then they're going to all fit in, and then they're going to all fill up, and then it's just going to become one point. So that removes the noise from that scale level. And again, I don't know, maybe that is going to be useful in dealing with the amount of noise, because you're going to just sit there and just modify epsilon and keep going, and you increase epsilon in increments, and you see when it is that a topological space has features and then doesn't have certain features. And if this feature goes away at a certain point and comes back, this again could just tell you more about the structure of the homology. I mean, even if we take, like, you know, something like a torus, right? Like, if we were to find out that data is arranged in a torus in 3 dimensions, you could then see that, oh, it's likely a torus because, you know, at a certain point, the homology is exactly the same. For a certain epsilon, the homology is exactly like a torus. So maybe at this point, the data structure looks like a torus. But again, that's only if we are able to perhaps remove a massive amount of noise at the very fine levels that these points, you know, if I superimpose the data set onto a torus, right? Maybe the data points are on the torus around here, whatever. Okay. those might not actually be points. They might just be clouds that became points when epsilon got big enough, and that when we zoom in, there's just noise in each one of these points. And dealing with that in another way would be almost possible, because how would you determine that this is noise and you should just consider it one point? But it would involve also perhaps some sort of pre-processing of the data if we want to do this for big data.